Objective: to understand Einstein's explanation of the photoelectric effect. Albert Einstein explained the observations of photoelectric effect for which he received the Nobel Prize in 1921. He explained the photoelectric effect taking into account Planck's quantum theory of electromagnetic radiation. Einstein called the packets of energy as photons. According to him, electrons are held to the metal by attractive forces of positive ions of the metal. To overcome these forces, photons of the light incident on the metal must possess a certain minimum energy so as to release an electron from the metal surface. Thus, when a photon of sufficient energy strikes an electron in the atom of the metal, it transforms its energy instantaneously to the electron and the electron is ejected without any time lag. From the quantum theory of radiation, we know that the energy of the incident photon is directly proportional to the frequency of the incident light. The minimum frequency that provides enough energy just to release an electron from the surface of the metal is called the threshold frequency, denoted as nu0. Hence, when a beam of light or photons strike the surface of the metal, electrons are ejected only if the incident photons have the frequency nu greater than the threshold frequency nu0. Let us assume that the frequency of the photon of the incident light nu is greater than the threshold frequency nu0. In other words, the striking photon has an energy equal to h nu and the minimum energy required to eject the electron is h nu0. As the energy of the incident photon h nu is greater than h nu0, the remaining energy, that is h nu minus h nu0, is imparted as kinetic energy to the electron. Thus, h nu minus h nu0 is equal to half mv square. Here, m is the mass of the electron and v is the velocity of the ejected electron. On rearranging the equation, we get h nu is equal to h nu naught plus half mv square. H nu naught is constant for a particular metal and is denoted as W naught, which is called work function. Now, the equation in terms of work function is as shown. Let us observe the values of work function for a few metals. Hence, if the energy possessed by the photon is high, the energy transferred to the electron is also high, and hence the kinetic energy of the ejected electrons is also high. In other words, greater the frequency of the incident light, greater is the kinetic energy of the ejected electron as shown in this graph. Lastly, greater the intensity of incident light or the number of photons that strike the metal, greater is the number of electrons ejected. For example, when less intense and more intense yellow light is incident on potassium metal separately, then a relatively greater number of electrons are ejected from potassium metal when irradiated with the light of higher intensity. Thus, the phenomenon of photoelectric effect was successfully explained by Einstein, which proved to be a strong evidence for the photon model of light. The phenomenon of photoelectric effect is used in CCD in digital cameras, photovoltaic cells, and photomultiplier tube. Let's summarize what we have learned. The photoelectric effect was successfully explained by Einstein using Planck's quantum theory. The kinetic energy of the ejected electrons is calculated by kinetic energy of the ejected electron, which is equal to h nu minus W naught. Photoelectric effect successfully explains the particle nature of light and proves to be a strong evidence for the photon model of light.